Hi, my name is Sam Smith, and today I'm going to talk about some work we've been doing to expand a dynamical theoretical framework for understanding the hydrologic cycle, which was first introduced by Liu et al. 2017. This framework, known as the local hydrologic cycle, is a hybrid approach which can leverage both the advantages of a traditional Eulerian moisture budget and a tracer-based Lagrangian analysis. I'll start by arguing for the relevance of the local hydrologic cycle, or LHC, and reviewing the basic framework, explaining how we expanded the original framework. After reviewing the LHC framework, I will show our results, which apply it to the historical and RCP 8.5 scenarios of the CESM large ensemble. Our results show that the dynamic contributions of LHC change are consistent with both a slowing and an upward and poleward shift of the general circulation. All our results today will be viewable in greater detail in a forthcoming paper submitted to Journal of Climate. The overarching question we set out to address with this work is, how does uncertainty in changes in the general circulation contribute to uncertainty in the hydrologic cycle change? This question is critical if we hope to improve our ability to predict hydrologic cycle change, primarily because the circulation response to climate change is the major source of uncertainty in future projections of the hydrologic cycle. However, isolating this circulation-driven or dynamic component of change from the more robust thermodynamic changes is not trivial, as the two components are tightly coupled in the nonlinear advection diffusion problem which controls the hydrologic cycle. This nonlinearity confounds some current efforts through the addition of complicated or nonlinear terms in the traditional moisture budget. Understanding dynamic changes is further complicated by the varied and compensating processes underlying them. Efforts to decompose dynamic changes often cannot distinguish between processes or require assumptions that are not valid for some regions, such as the quasi-geostrophic-based decomposition shown on the right. Moreover, few of these efforts extend to the dry end of the hydrologic cycle. Thus, a framework is needed which can both cleanly separate thermodynamic and dynamic contributions and which can be further decomposed to probe the underlying dynamic changes across the hydrologic cycle. For this work, we focus on developing such a framework for the LHC, which is one aspect of the broader atmospheric hydrologic cycle. Physically, the LHC is the net precipitation or evaporation connected to zonally anomalous moisture or dryness. However, the zonal reference state used for the LHC is not the zonal mean. Rather, we use a Lagrangian reference state or background state found by zonalizing a zonally varying column water vapor contour, shown as the thick red line. This is accomplished by determining the latitude, termed the equivalent latitude, which divides equatorward dry contour excursions, shown in tan, and poleward moist contour excursions, shown in teal, into regions of equal area. By establishing a wave-free background state, we are more strongly constrained to the Clausius-Clapeyron relation than the zonal mean column water vapor. In our paper, we develop a scaling relation allowing us to predict the future background state, which also confirms its thermodynamic nature. We show here the log rate of change for the background state compared to the zonal mean. Note that the latter varies considerably more with latitude. This improvement is crucial in obtaining a clean separation between dynamic and thermodynamic changes. Once we have determined the background state for a given column water vapor field, we then integrate net precipitation and the moisture flux convergence over the areas enclosed by the moist and dry excursions. The integrated net precipitation is the LHC, and the impact of this areal integration is that the LHC captures precipitation and evaporation by large moist and dry meridional intrusions. Since such events often produce strong precipitation and evaporation, the LHC agrees well spatially with other measures of the higher moments of the hydrologic cycle, such as the 99.9th percentile of net precipitation, shown here. The shading represents the wintertime CMIP 5 99.9th percentile of net precipitation, and the contours display the wet component of the LHC. This highlights another important advantage of the LHC approach, that it can be used to study both ends of the hydrologic cycle because moist and dry excursions are computed separately. For this work, we analyzed the LHC in the CESM version 1 large ensemble, a 40-member initial condition ensemble of fully coupled simulations, with some details listed here. Further details on the CESM version 1 large ensemble can be found in K et al. 2014. For this work, we compute the LHC and its components from the 6 hourly fields listed here, and we take the 1990 to 2005 average of these quantities as the present-day annual mean, and the 2071 to 2080 average as the RCP 8.5 annual mean. The present-day LHC for the CESM large ensemble is depicted here as the shading, with wet and dry distributions shown separately. Black arrows represent the moisture-weighted vertical mean velocity. Gray shading represents regions of large orography, which are presently not well handled by the LHC routine and should be interpreted with care. The present-day annual mean wet LHC is large near the equator, with the global maximum near the Pacific warm pool, and other local maxima near storm tracks. The present-day dry LHC emphasizes the eastern margins of subtropical highs. The spatial distribution of both fields is heavily influenced by the low-level flow. We now turn to RCP 8.5 fractional changes in the LHC. Here, stippling indicates regions where fewer than 85% of ensemble members agree on the sign of the change. Under RCP 8.5, the wet LHC is suppressed in the subtropics, but fairly uniformly enhanced elsewhere. A strong local maxima exists in the vicinity of the North Atlantic warming hole, which will be discussed in more detail later. The dry LHC is likewise enhanced, excepting some weak suppression in the tropical Pacific. The largest increases in the dry LHC appear at the margins of subtropical dry zones, consistent with a poleward expansion. Now that we have established the concept of the LHC and illustrated some of its advantages, we will decompose its climatology and projected changes. We accomplish this through two independent approaches. First, we utilize the LHC framework to transform the traditional moisture budget into two separate budgets for the wet and dry LHC. The results, derived more rigorously in our paper, partition the LHC into contributions from background state moisture convergence and advective processes, the latter consisting of both a meridional moisture flux and a zonal moisture flux convergence. When examining changes in the LHC, changes in background state moisture convergence can also be further decomposed into thermodynamic contributions and contributions from overturning processes. Results for the present-day LHC generally confirm that we are able to partition the LHC into background convergence and advection contributions, with the former dominating in the tropics and subtropics, and the latter dominating in the mid-latitudes. The two advective terms, the meridional flux and the zonal flux convergence, offset one another in the mid-latitudes, due to the predominantly rotational nature of low-level mid-latitude flow. We will examine fractional contributions of each budget term to the total RCP 8.5 change in the LHC. These contributions are broadly consistent with current understanding of the connections between the general circulation and the hydrologic cycle. Contributions from thermodynamic processes broadly act to enhance both the wet and the dry LHC at or around the Clausius-Clapeyron rate of 7.5% per Kelvin, with some zonal variations in the wet LHC. Overturning tends to largely dynamically suppress both the wet and dry LHC, consistent with the projected weakening of the overturning circulation. Overall, the meridional flux terms act to enhance the LHC. Moist fluxes enhance the wet LHC poleward of present-day storm track regions, consistent with the poleward shift. The contributions from the zonal flux convergence are more varied and notably more uncertain than the other components. However, some patterns emerge. These contributions increase the wet LHC in jet exit regions, particularly the North Atlantic, and decrease it in jet entrance regions. The zonal flux convergence contributions increase the dry LHC at the margins of subtropical anticyclones, showing it is crucial in communicating the impacts of subtropical expansion to the LHC. Despite the success of this approach in highlighting the dynamical impacts on the hydrologic cycle, the advective terms depicted here are not purely dynamic because their magnitude depends on the background moisture gradient, which we have already shown to be a thermodynamic quantity. Thus, we require a second approach to more cleanly separate thermodynamic and dynamic influences. In this approach for decomposing the LHC, we utilize a semi-empirical linear relationship found by Liu et al. 2018 for the wet LHC, which we modify and apply to the dry LHC. This scaling allows us to decompose the LHC more cleanly as the product of the background moisture gradient, the mixing length squared, and the cycling rate. The mixing length measures the meridional distance moisture excursions are mixed over before being damped by the LHC, and the cycling rate measures the rate at which that damping occurs. The wet LHC also includes the participation ratio in its scaling. The participation ratio measures the fraction of moist excursions damped by the LHC, since moist excursions are not everywhere condensed into precipitation. Since evaporation does not have a temperature threshold, as does condensation, the dry LHC does not need this term. The present-day annual mean scaling for the LHC is depicted here. The mixing length highlights regions which play a prominent role in exporting and transporting moisture and dryness. For wet regions, this is near storm tracks and over the Pacific warm pool. For dry regions, it tends to be in the subtropics. By driving filamentation and elongating the mixing length, wave breaking plays an important role in determining the mixing length's spatial distribution. Wave breaking is also captured in a different way by the cycling rates, which tend to be small in the tropics and subtropics where wave lifetimes are longer. The moist cycling rate is especially high near high latitude orography, where orographic lifting further reduces wave lifetimes. As a measure of the ability of a circulation to convert water vapor into precipitation, the participation ratio roughly captures regions of instability. It is high in the deep tropics in regions of convective instability, low in the subtropics, and it has some modest increases near storm tracks in regions of baroclinic instability. RCP 8.5 fractional changes in scaling terms can be summed to recover the fractional changes in LHC, with the thermodynamic term included in both wet and dry changes, and with the mixing length weighted twice. Note that the thermodynamic term is zonally uniform and in better agreement with the CC relation than the budget-based thermodynamic contributions. The moist mixing length decreases in many subtropical and mid-latitude regions, while increasing further poleward, reflecting the poleward shift of the storm tracks and expansion of the subtropics. This subtropical expansion results in strong increases in dry mixing length across much of the mid-latitudes, leading to an asymmetric response of the mixing length between wet and dry ends of the hydrologic cycle. In agreement with Liu et al. 2017 and earlier work suggesting a slowdown in the hydrologic cycle, the moist cycling rate slows down almost everywhere. Interestingly, this slowdown also extends to the dry cycling rate, potentially reflecting an overall weakening of the general circulation. Finally, the participation ratio decreases throughout much of the globe, suggesting that the threshold for participating in the LHC increases faster than the LHC itself. An important exception is the North Atlantic, which acts as the primary driver behind superclasius-Clapeyron increases seen in the wet LHC here. This increase likely reflects the effects of cooler sea surface temperatures, triggering condensation in warmer air advected over the North Atlantic warming hole. For this work, we've extended the hybrid Eulerian-Lagrangian dynamical framework known as the local hydrologic cycle to a zonally varying formulation with closed budget equations. We also extend work for the wet end of the hydrologic cycle to the dry end, and we apply this framework to the CESM large ensemble. Our results show that the background state is better constrained to the Clausius-Clapeyron relation than the zonal mean, yielding better separation between thermodynamics and dynamics. The dynamic changes seen here are broadly consistent with our understanding of future changes in the general circulation, demonstrating that the LHC framework diagnoses circulation impacts on the hydrologic cycle. Notably, the hydrologic cycling rate slows down on both moist and dry ends of the hydrologic cycle. The moist mixing length generally contracts in the mid-latitudes, while the dry mixing length expands, highlighting the asymmetric impacts of subtropical expansion. Further work is needed to contextualize the dry LHC changes seen here, as changes in dryness are not usually examined on 6-hourly timescales. Since the LHC framework shows promise in identifying how the circulation impacts the hydrologic cycle, we hope future work will focus on using observational data to identify model biases and using CMIP6 data to explain intermodal differences. Thank you.